Hi, I'm Chris Carbone, structural engineer with Bensonwood. We are out of Walpole, New Hampshire, which is the southwest corner of New Hampshire. I started working there in 2002, and I have quite a number of slides to get through, so I'm going to try to talk quickly and get you guys to lunch on time. About 9.5 seconds a slide, so it's going to be fast. Hold on to your hats. So I started here in 2002. It was the summer between my 2 years at MIT as a graduate student. I went to my advisor that spring, and I said, what should I do this summer? He said, well, you like wood, you like New Hampshire. My wife's high school boyfriend is a project manager at this cool company called Bensonwood, so why don't you go work there? And so he hooked me up with an internship in the timber framing shop. So we had two big jobs there that summer, one down in Tewksbury, Massachusetts, and one here at Stratton, Vermont. So most of the summer, I spent the time sweeping up the floor, cleaning the wood chips out of the grinder that feeds the boilers. But the last couple of weeks, they let me out on site, and I joined the crew, mostly, again, sweeping the deck and things like that. The story, though, of Bensonwood goes back to 1972. This is not Portland, although it looks a little like it, I think, where Ted and his brother started a company basically doing cabinetry. And when they didn't have work, they would make trade offers to tear down old barns to get salvage materials. And in doing that, they learned how rugged the joinery was of the New England timber frame tradition, which came over from the colonists in the 1700s. So they amassed a large amount of salvage eastern white pine, salvage oak, I believe, a bunch of salvage material. And eventually, they convinced a client to entrust them to build the first timber frame project in New Hampshire in over 100 years. It was covered by, I believe, New Hampshire Public Television or Public Radio at the time, and the jobs continued to come because of the beauty of the timber frame, the exposed structure, and there was sort of the back to the earth movement in the 70s where people wanted to be with and touch wood. But really, Ted had always had this vision of reviving the timber frame craft, but doing it in a shop-built environment where we could control quality, where we control temperature, music, all those good things that we can do in a shop that the mosquitoes buzzing in your ears don't happen as much. He, with a number of other people, started the Timber Framers Guild. And through connections in the Timber Framers Guild is here, and if you're looking for people to put up your mass timber projects, they're certainly well qualified. They know how to use big tools. They know how to raise big panels, whether they're made of foam or wood, and they understand the value of planning and logistics and stuff. But anyway, the Timber Framers Guild connections hooked Ted up with this Japanese timber framer, Ishikawa, who came to New Hampshire and spent a year with the woodchucks, basically teaching them that we don't peg our tenons with rebar, we know how to plane. He would host nighttime workshops with not only the employees, but their wives and families and other people in town. And I remember hearing the story when he explained to them how smooth a planer should be. He said through a translator, so smooth that even the flies and the mosquitoes slip. And that was something that just opened these New Hampshire folks, their mind to the possibility of a higher quality. To be tied back to people who built the temples 1,400 years ago is pretty amazing. 1,400, right? Yeah, 700 BC. Pretty amazing. But Ted was also very intrigued by new technology and the power of CAD. And fortunately, he had a genius living down the road. And he bought this guy a computer. His name is Reese Atchison. The first thing Reese did was take the computer apart. And Ted walked in and almost lost it. But so Reese wrote a computer program that could actually calculate compound angles for the timber framers to work from. So not just the angles of the roof and the primary angle of the hip or the valley rafter, but the internal angles inside of these joints and the way that a jack rafter would come in. These were things that are very difficult to work out in your head. So using a machine and writing his own CAD program to do that was really something that set Bensonwood apart from a lot of other timber framers in the early days and enabled us to take on and tackle more complex architecture. When you take on more complex architecture, you need engineering to stand behind it. There's some risk there. And so in 1985, Ted hired Ben Brungraber, who was the lead engineer at Bensonwood for 20 years. Ben was particularly interested in traditional joinery. He had done his PhD research in peg tenons, and he really sort of brought Bensonwood to the beauty of spline joinery, where you're using hardwood, which is stronger than softwood most of the times, to connect members, and not tenons as much, but really spline joinery, which is an ancient Japanese technique as well. Keyed beams was another big thing that we got into there in the 90s, where you're building up a bigger beam out of two smaller beams. It's kind of an old-fashioned way to do it, where you proportion the spacing of the shear keys, the wooden shear keys, or you could use iron shear keys or whatever. But basically, you proportion them based on the integrated area of the triangles, and they prevent the beams from slipping between the layers. It's extremely labor-intensive to make these because you have to cut every single notch, and the fits have to be basically watertight. You also generally want to use some dry material, which can be achieved by salvage or kiln drying, so that the effects of shrinkage and movement over time are mitigated there. We got into making a bunch of glued composites as well. The glue lam industry is great. You can buy curved glue lams, but it does get difficult to buy glue lams when the radiuses get tight, so because the lamella gets so small. So you need to work with a pretty good glue lam manufacturer to make those. They are more available these days, but we started making them ourselves and learned a bunch about composite action and getting that out of glued composites. This is a project I did in Commerce, Georgia for Huber, where the glue chemists sit around and sniff glue. So we're using southern pine glue lams as the post and eastern white pine glue lams as, not glue lams, eastern white pine solid sawn as the braces and the struts up to southern pine rafters. And at the foyer of this building, we used a large eastern white pine log tree, which we peeled with a pressure washer. That's a secret if you want to debark a tree really well without messing up the cambium layer, is use a pressure washer and get the really good nozzle that sort of rotates around and sort of go at it along the grain. It'll sort of blow the bark right off. Anyway, southern pine glue lam cords, red oak struts, steel rods with adjustable fittings that we invented, and Advantex spline going through that post. Not really a tension member in that case, more just to carry the truss and give us something safe to land on. What happened here? Okay, and then cantilevers. Cantilevers are great, and glue lams can do a lot with cantilevers. In this project, we quarter sawn spruce logs, which you can see in the core of the building. We keyed them together with hardwood cherry keys in the middle and big bolts to clamp them all together. And then this thing cruciforms off in two directions overlooking Sugarbush, Vermont. No, so that's sort of what I walked into in the engineering office, like all this really cool, traditional, modern joinery, learning structures, learning wood, learning the properties and how it's different depending on which way you push and pull on it, and different species are different, so you can use one in one application, learn about moisture and shrinkage and all those great things. But the company was always trying to not just improve the structure, but improve the entire building system and the building process. And so we embarked on something that we're now calling open building, and we stole that term from a guy named John Habraken, who came over and visited our company when he was a visiting professor at MIT in the 80s. And what that allows us to do is break the buildings down and into their various elements and then bring them to the site, assemble them rapidly, and provide spaces and chases for mechanicals and systems and stuff. So we went from building a frame in 12 days in the 70s to a frame with the panels in 2 weeks in the early or 90s there. And then here in 2008, we did a frame with panels with siding on and bathroom pods basically all finished in a matter of 3 weeks there. But the real problem has always been, how do you... That still work? Okay, came back. That's good. How do you enclose the timber frame? And if we didn't figure out a way to enclose a timber frame, the timber frame revival would never have happened. So they started doing it by basically infill framing, putting in insulation in between the studs, and they realized pretty quickly that that was not very good. It was really no better than the colonists had done, except for there might have been some insulation in there. But airflows through that assembly were pretty significant, and the assembly itself was pretty minimal in terms of what the R value was. So Ted and a couple other people started looking into SIPs, structural insulated panels, which are foam laminated OSB on both sides. They call them stress skin panels. And really, there's a whole industry now that has developed load values for gravity, axial, lateral, all the good stuff. And it is a pretty good system if you forgive the toxicity of some of the foams out there, and you're building with a full timber frame where you've got basically structure every 4 feet, and you can get continuous insulation around the building. The question is always, how do these things come together at the corners and at the seams of these panels? And if you don't do a good job paying attention to details, to seal the building up, you're going to have air, usually moisture-laden air, moving through your building, turning the outer skin into oatmeal in our climate, which is not a pretty thing to look at. So here are those two pioneers of open building, John Hobrock and Stuart Brand. Stuart Brand, in my opinion, the book How Buildings Learn is a must-read for any architecture, engineering, construction, poet, whoever should read this building. But I love this picture where he's taken the systems, the 6 S's, as he says, the stuff, the space, the services, the structure, the skin, and the site, and drawn lines. And they all have different rates of change, different lifespans. So the site really never changes. The structure changes maybe once or twice in a building's lifespan. And then all the other ones are lifespans on the order of 30 to maybe 30 years to maybe 30 days, depending on what stuff you're buying. And that we should respect each of these systems, design them separately, design them so that they're separate from each other, and you can change them in a smart way. So we talked about it in 1994 more as a theory, and by 2006 we were realizing it pretty well in practice. So there's a sketch in 94 and a CAD model export and a rendering of our timber frame, panelized system. And so how did we, well, this is not a new idea, and it's great to see all these tall buildings, and I really hope that we can maintain this separation of MEPs and structure and skin and really focus on optimizing each one within its own system. So how do we do it? We do it through a variety of open-built strategies, or that's what we're calling them. The first one, old carpenter's adage, measure twice, cut once, so we build it twice, virtual, and then we build it actually. We actually have a team in our company of 6 guys. We call them the VFab team, which is virtual fabrication. I think it's very fabulous, but they're really great guys. And what they do is they take my engineering model, which doesn't have every stud, doesn't have every rafter, but it has a description on it. It says studs at 2 feet, and it's this stud or that stud. And they turn it through automated processes into a fully elaborated structural model. And then they overlay it with MEP information that we get, either we develop in-house or we get from a subcontractor. We look for conflicts, and hopefully we find them first digitally before we build them in the shop or then take the panels to the site. This information is tied to CNC fabrication machine. That is a key to anything. This is the second oldest Hundiger on the continent. It's still running. We need a new one. I'm taking donations, but they are kind of expensive machines, and they're big too. You need a big place to put them. But it's cool to see this in the lower left there. We took the CAD model I mean, you can do all those, CAD animations of the tool paths and stuff, but you can't really do that until you know what you want to do. So we've taken some key parts, like the big universal mill, and we've put it into our digital library so that the architects and the engineers can quickly see that if they want to put a mortise in at an angle, the universal mill is not going to clip the timber. They don't have to go all the way until you elaborate the whole thing. We also have a speed cut machine, also made by Hundiger, and that cuts all of our small stuff, our dimensional lumber, I-joists, LVL, that sort of thing. It does also print the part numbers on each single one, and so those part numbers then automatically show up in our shop drawings, and then again in our site drawings when we look at bundles. So what we're trying to do is take 50,000 pieces that go into a typical home and turn it into 50 high-value elements, whether they're windows or cabinets, which is nothing new. You wouldn't build your window on site anymore, but we're doing with floors and walls and doors and boilers and things like that. In the lower right there's a floor system with radiant heat tubes in it and recessed can lights and electrical, all set. It's upside down. It's easy to put in for the plumber. He's not standing on a ladder. What we try to do is optimize. So we've been using foam core panels for a lot of years, throwing a lot of foam into dumpsters. When you cut out the window openings, you generate a lot of waste. Seeing the foam beads that, 5 minutes? Impossible. Seeing the foam beads that skim lakes, and it's just nasty stuff. So we decided we were going to build a cellulose panel, a cellulose insulated panel. We use I-studs. We use engineered I-joists as studs for axial capacity. They're deep. They're 9.5 inches, R35. This is the Bensonwood core wall. It's a 3-story wood frame wall. And what I'm going to do here is just jump right ahead and sort of go 2 seconds. So boiler rooms, flat pack shipping. This is where we learned how to pick up big panels. And it's true. The site is the worst place to control quality and cost and things like that. So mass timber, that's really what we're supposed to be talking about in the next 4 minutes. So I did a number of glue lam projects in like 2012 time. There's a big 56-foot clear span dug for a glue lam, spans over a concession stand at our baseball pavilion. That's a 56,000-pound tension capacity joint in the upper left. This next project was a steeple that got hit by lightning. It was a masonry steeple, 90 feet tall, and when they looked at the cost of replacing masonry with masonry, it was pretty much cost prohibitive, and the dead weight of the thing was also pretty significant at masonry. So we were able to prefabricate an entire steeple 40 feet tall. The steeple sat at 40 feet, so it got up to about 90. In our factory with the board sheathing on it and with the ladder inside of it so you could go unhook the crane. That was a sort of a late-breaking thought. Here's a big carport at a lodge in Pennsylvania. The tolerances on the anchor bolts in the CMU was 1/8 of an inch. So thinking about tolerances and making sure your steel's going to fit is very important. We almost always will pre-fit our steel in the shop to make sure it fits and make any small adjustments in our shop so that when we're doing it on site, it goes smooth. So in 2012, we did our first couple CLT projects. This is a project in Idaho, I believe, where CLTs are working as 3-story shear walls. You can see them dropping down through the deck and we actually did some pre-cutting of holes and doors for mechanicals and the door to the master bedroom. We've done a number of boutique CLT projects, I would call them, very small projects. This is an art gallery in Brooklyn. If you build in New York City, you should get a building permit. Otherwise, you might have to build with the door down and the diesel running. So you can see the door is actually cracked there. And we had carbon monoxide sensors around our guys' necks. But beautiful project. Here's a small little entry to a school where they took advantage of CLT's 2-way span capability, make those cantilevers on that nasty galvanized steel frame. This thing just locked up. There's just a detail of how they come together, the plywood spline that gussets into a routed-in groove. I did an art installation with some really talented architects, Aaron and Yasmin, for a project that's first showed in Boston. It will be at the National Building Museum this coming fall, I believe. And this is a yoga studio in Baltimore where they basically gutted an old garage, I believe, and put in a second-story CLT platform for people to do yoga on. There's a picture of the edge of it when it was all finished. And the top of it, we just had to plan out where the columns were and make the panel seams there so we could splice things around it. Here's a CLT garage that engineer, Jim DiStefano, did for himself. We provided the CLT, and he had Timber Framers Guild people, I believe, cut the eastern white pine timber trusses that it sits on. Big project we did last summer is called the Common Ground High School. It's America's oldest environmental charter school. We did it with Gray Organsky Architects. Alan Organsky is a professor at Yale, and they are in New Haven. This is a lot of CLT with our open-built wall panel, the R35 wall panel. Here it is before the siding went on. Here it is sort of a couple days into construction. On the north side of the, well, it has an elevator shaft, a CLT elevator shaft that does not primarily contribute to the lateral system. That's all dealt with shear walls, but it is sequestering carbon the whole way. It does get fire rated by sheetrock on both sides. 66-foot clear span timber trusses with steel rods that change their diameters to reflect the tension in them as they get smaller towards the middle. That one in the foreground becomes the clerestory windows for the multipurpose room. The one in the background supports the second floor system and the roof at the junction of the north and the south. That one in the foreground there landed on a sort of queen post modified truss that spanned 25 feet over a bifold door. So landing trusses on trusses, that's something fun for engineers to do. Building trusses in our shop is something fun for our company to do. Here are some big timber rafters. They're 11 by 18. Going in on site, there's Toby, there's Thomas. And here's a picture of the space from the inside with the light coming in through the clerestory under construction. They're about a month away from getting their CO. They've whitewashed all of the timber. It looks beautiful. And so that's the north side of the building. The south side of the building is this great CLT atrium space with a beautiful stairway coming down into it, real sculptural thing. We're able to prefabricate that, engineer that, prefabricate that in our shop, ship it to the site, install it rather quickly. One of the struggles that we had was where the cross grain was exposed. We had a lot of tear out on the product, and you can't have that in a school project because people's pencils and fingers will get caught in there. So that all got filled with putty and looks actually pretty good in the end because the whitewash sort of blends the whole thing. On the south side of the building, we did an innovative CLT box beam as a roof panel. So we used a CLT bottom skin to handle the tension. We used I-purlins as the webs of the box panel and 5/8 OSB on the top, the zip system. Filled it up with dense packed cellulose and have a vapor control layer in there for basically an R53 panel. So that's what it looks like. Beware of architects who change opening sizes in late stages of design, so that we had to sister up a truss to the back side of a CLT header because that opening was supposed to be 3 feet smaller, or that's what I thought. When we made those roof panels, we did all of the electrical in the shop as well. So here's a little lesson learned. A 4-inch junction box is like 4 1/8. So if you're going to CNC it at 4 1/8 or 4 1/4. The escutcheon plate will cover it. This is some vapor control. We did a lot of hydrothermal modeling to be sure that our system would work in this environment. And we actually spaced the screws that connect the purlins to the bottom skin, just like those shear keyed beams to reflect the shear flow in the beam over the clear span. We built in the light shelves at the clerestories, and these things were heavy. They were like 6,000 pounds. So we had to use 2 cranes to pick them up inside of our shop. This is a picture of the electrical penetrations going up through that vapor members. This is how we tagged them in our shop. They come with stickers on them, barcodes, those sorts of things. More pictures of the electrical conduit going in there. There's the electrician. I'm just sort of rolling through. There's my engineering intern. I got to say this lesson. It's worth sticking around for lunch, or not for lunch. So they wanted to pre-drill and use the machine to locate where all of those fasteners were, because there were like 35,000 screws in this roof system, or some obscene amount. And I said, sure, that's a great idea. It'll save time. And so I went in the structural model, or our build model, and I looked at the diameter, and it was like 1/8 of an inch. I was like, okay, we're going to pre-drill 1/8 of an inch, 1/4 inch screw, no problem. Well, they got to site, and the guy calls me on his cell phone. He's like, this thing is deflecting 3/4 of an inch. You told me it was going to be 1/4 of an inch. I said, shit, that's not good. So first thing I did was I checked to make sure that, yes, I did design it so that the 14-inch member by itself could handle the load, and I didn't need the composite action for the thing not to collapse. So that made me sleep a lot better. But I did have a window issue where somebody else had to install windows into an RO that was defined. So I wanted to sort of figure out, well, what is the deflection, and is it going to continue? Is it going to get worse or not? And so I went down to the machine operator. I said, what did you use to drill those things? And he pulls out the 1/4 inch bit. I said, who told you to do that? Well, anyway, 1/4 inch bit, the screw diameter is actually 0.24 inches if you look closely at a Simpson screw. So there's a 0.06 difference there. And when you look at the deflected shape and interlayer slip of that 0.06, when you added it all up, that equaled the 3/4 inch deflection, like geometrically. So I was like, okay, this is good. That means we're at the point where the screws have started to engage, and I'm going to get my composite action now. So to convince myself, I filled up a kiddie pool, got up on the roof, had my project manager underneath with a laser, and filled it up, started jumping up and down, and he just couldn't measure any more deflection where I had calculated how much deflection that amount of water was supposed to deflect, and it wasn't even getting close to that without composite action. So it's working in composite action now. All we had to do was rabbet out the windowsill, which was already beefed up for wind loads. I do need to talk about MEP systems. If you want to go to lunch, I'm sure it's good. But sprinklers are a pain in the butt for me. They are complicated. When they go from inside to outside, they need to pitch. And if the concrete is off that you're setting your wall panels on, then that will affect where any hole that you drilled for a sprinkler system winds up being. So this is some screenshots of the MEP coordination. It was a nightmare on this job because things were very entwined in that second floor system. Those are some beams that we looked at drilling, and in the end we only drilled like 4 or 5 holes, and one of them was wrong. We've heard a lot about shrinkage. This is a project right at Hampshire College where we installed glue lams and CLT decking, not CLT, glue lams and 2x or 3x decking, and we were promised that they would protect and get the roof on. You can see how complicated that roof system is, extremely crinkly. Well, that promise didn't come to fruition. The building sat, the floor got rained on for a number of weeks in the summer, and the building actually started pushing itself apart. It grew 2 inches in each direction. This is a big timber girder that's falling out of its pocket there. I don't know if you can see that, but there's no support on that. Steel was pulling itself apart. So we took moisture readings. It did correspond to what it would have been doing if it got wet. And we had to go in and actually remove things, come along the whole system back together, and reattach the whole diaphragm with special nail system. This is what it looks like underneath. And I was going to talk about UMass, but I'll just say that I won't. I'll refer Tom Chung to answer any question about UMass, or Robert Malchik, who's the engineer. And it's been a pleasure working with those guys.